In the world of 3D reconstruction, one challenge has remained stubbornly persistent: scaling high-quality, feed-forward models to handle large-scale scenes with hundreds of input views, without sacrificing speed or fidelity. Traditional transformer-based approaches struggle here. As the number of input views increases, so does the sequence length of tokens, leading to quadratic growth in computational cost due to self-attention. This makes it nearly impossible to process more than a few dozen views efficiently, let alone scale to real-world scenes with 250-plus frames. Enter multi-view pyramid transformer, a novel architecture designed not just to overcome this bottleneck, but to fundamentally rethink how we reason across multiple views. At its core, MVP is built on a deceptively simple idea: look broader to see the whole, look finer to see the details. This principle, long used in computer vision, is now applied with precision to multi-view reasoning through a dual hierarchical attention mechanism, a powerful synergy of two complementary design axes. First, the intra-view hierarchy gradually expands the model's perspective. It begins with local, frame-wise attention, extracting fine geometric details from individual images. Then, in the second stage, it groups views into clusters, applying group-wise attention to capture mid-range spatial relationships. Finally, in the third stage, it unifies all views under a single global attention window, forming a coherent, consistent 3D scene representation. Simultaneously, the intra-view hierarchy operates on the spatial dimension within each image. As the network progresses through layers, image tokens are progressively merged, reducing resolution by a factor of 4 at each stage while doubling the feature dimension. This creates a multi-scale feature pyramid, where early layers focus on fine-grained textures and edges, and later layers build coarse, semantically rich representations with wide receptive fields. Together, these two hierarchies create a balanced trade-off: local precision and global coherence, all while keeping the number of tokens involved in attention under control. Why does this matter? Because attention dilution, the phenomenon where global attention becomes unstable and ineffective as context grows longer, is a major failure mode in long-sequence modeling. With too many views, the attention distribution spreads thin, losing its ability to align features consistently across views. MVP avoids this by limiting attention scope at early stages, ensuring that each interaction remains meaningful and focused. The result? A model that doesn't just scale, it thrives under scale. We tested MVP on the DL3DV dataset, a large-scale benchmark with scenes containing 250 to 350 frames. With 32 input views, our method already outperforms prior feed-forward models in both PSNR and SSIM. But the real breakthrough comes when we push to 128 and even 256 views, settings where most baselines fail entirely. On 256 views, long LRM runs out of memory. ILRM's performance degrades sharply, showing diminishing returns as more views are added. Meanwhile, MVP maintains consistent improvements in reconstruction quality, reaching within 0.7 dB of optimization-based 3D Gaussian splatting, but over 250 times faster. And inference time? Under 1 second on a single H100 GPU, even for 256 views at 960 times 540 resolution. But MVP isn't just fast, it's robust. In zero-shot generalization tests on tanks and temples and MIPNI RF 360, our method consistently exceeds the baselines across all view counts, with the gap widening as input complexity increases. It generalizes not just to new scenes, but to longer input sequences. We also evaluated performance on low-resolution settings using real estate 10K, where our coarse variant already surpasses prior work. With finer patch sizes, our fine variant achieves state-of-the-art results in both metrics and visual quality. To understand how MVP achieves such strong multi-view consistency, we visualized attention patterns across stages. In the group-wise stage, attention focuses on geometrically aligned regions within the same group, capturing local correspondences. In the global stage, even though tokens are coarse, the model still attends to semantically consistent areas across distant views. This proves that MVP doesn't just aggregate information, it learns meaningful relationships. Ablation studies confirm the necessity of both hierarchies. Removing the intra-view hierarchy leads to over 6 times higher latency at 256 views. Eliminating the intra-view hierarchy causes out-of-memory errors. Even reversing the hierarchy, starting global and ending local, results in a dramatic drop in performance. These findings underscore that the order of reasoning matters. Fine to coarse, local to global isn't just a design choice, it's a principle. Beyond reconstruction, MVP's architecture is generalizable. It can be adapted to dynamic scenes with temporal modeling, or enhanced with geometry supervision to improve 3D accuracy beyond what view synthesis alone can achieve. In short, MVP redefines what's possible in multi-view 3D reconstruction. It combines scalability, efficiency, and high-quality output in a single, unified framework. By embracing hierarchical reasoning, both across views and within images, it achieves what previous models could not: fast, accurate, and consistent reconstruction from hundreds of views in a single forward pass. This isn't just an incremental improvement. It's a new paradigm, one where we no longer trade speed for quality, nor scalability for consistency. Instead, we look coarser to see broader and look finer to see deeper, and in doing so, we see the whole scene clearly.